Okay, in this chapter, we're going to talk about antiderivatives. In this first section, we're only going to think about things graphically and numerically. Hopefully, we can gain some intuition for how these things work. And of course, we'll be working symbolically very soon in the next section. So to start, let's talk about what an antiderivative is. We say that the function capital F is an antiderivative of the function lowercase f if capital F prime is equal to little f of x. So let's take a look at an example, of course. We could say first that x squared is an antiderivative of the function 2x. And that would be true because the derivative of x squared is 2x. You notice one strange thing about the definition, which we normally don't see in a mathematical definition. Here we have this n antiderivative. The reason why we say n and not the is because the antiderivative is not unique. For example, x squared plus 1 is an antiderivative of 2x as well. So is x squared plus a million. Right? All of those functions are functions whose derivative is 2x. Okay? In fact, it is true that all antiderivatives of 2x will be of the form x squared plus a constant. It may not be obvious why that's true, but it is true. Okay, so now let's take a look at how we want to approach these in this section. As I said, we're doing this graphically or numerically. Okay, here I'm going to give a graph of a function f prime. It could be 1, 2, 3, 4, 5. And then the function is going to look like this. It's going to be equal to 1 from 0 to 2. And then it's going to go down like this. This is going to be my function f prime of x. Okay, so we're just going to go from a picture here. Now we want to sketch a graph of the function f with f of 0 equaling 0. Okay, so f is supposed to be a function whose derivative is f prime. Okay. So let's draw our graph again. 1, 2, 3, 4, 5. And now note, let's go back and look at f prime. Note that f prime is equal to 1 for the first two numbers, right? From 0 to 2, on that entire interval, f is equal to 1. F prime is equal to 1. That means f itself must have a slope of 1 from 0 to 2. Now f of 0 is supposed to be 0, so we must start there, where I just drew the dot. And now I want a line of slope 1 as we go to 2. Okay, so that has to be what f looks like. Now we see, looking back at f prime, right? Now let's look at this portion, the second part. Now we have that f prime is decreasing, so the slope is decreasing, and we have a slope of 0 at 4. So how do we represent that? Well, now we're not going to grow, our slope is not going to be 1 anymore, right? Our slope is 1 here, but our slope needs to decrease and top out at 4. Right? We have to have a maximum at 4, given that f of 4 in the previous, or f prime of 4 is 0. So this is an example of such a function f, a function whose derivative looks like the first picture on the left. Now, this is not unique, right? Instead, we could want f of 0 to be equal to 1 instead. How would I draw that? Well, all I'm doing here actually is shifting the whole picture up by 1. this would be a different f. So this is f with f prime of 0 equaling 0, and this could be an f with f prime of 0 equaling 1. In both cases, the derivative is this picture over here. Okay, let's do some more examples like this. I'm going to sketch again an f prime function. Let's see, this is 2, -2. We'll go 1, 2, 3. Okay. We are going to be a straight line going from here to here. And then we want a straight line that goes down to there. Okay, so this is my function f prime. So that's the derivative. Okay. We want to sketch a graph of f of x. And we want 1 with f of 0 equaling 0, 1 with f of 0 equaling 1, and 1 with f of 0 equaling 2. Okay, so let's think about what's happening here. All right, now note that the function f prime is piecewise linear. By that I mean piecewise it's a straight line. Now straight lines are things something times x, right? Something times x happens to have as its antiderivative something times x squared, right? The antiderivative of a function a times x is a over 2 x squared. So that means that our graph is going to be piecewise quadratic. These are going to be pieces of parabolas. Now, let's think about what we have going on here. We have a negative slope. So I'm going to draw what I want for my slope to be here, right? We have a negative slope here because the derivative is negative. Then the derivative is positive. Then the derivative is negative again. Or sorry, it's still positive, but it's going down. And then the derivative is negative. Again, from 3 to 4. Okay, so first off, we know from here to here, right? We're going to start at 0. We got to go down some, but then we got to start coming back up. And we got to cross there. Now, why do I know that it's going to be equal to 0 at 2? I know it's going to be equal to 0 at 2 because of the integration theory that we learned, right? This is actually keeping track of the area underneath the curve. And by symmetry, the total area between 0 and 2 is 0. So, right, that I know that the integral from 0 to 1 of f prime of x dx is equal to 0 by the picture, but that's also equal to capital F of 2 minus capital F of 0 by the fundamental theorem of calculus. So that implies that f of 2 and f of 0 must be the same. So that's why I know I come right back up to here. Then, of course, by the symmetry here, I kind of want the exact same picture, but above for 4, right? And f of 4 is equal to 0 because the total area from 0 to 4 is again 0. So this is f with f of 0 equaling 0. Now, if I want f of 0 equaling 1, all I'm doing is I'm shifting this picture up 1 unit. So let's say this is 1 and this is 2. So I just shift this picture up 1 unit. It should be perfect, but of course my drawing is not exactly perfect. So this is f with f of 0 equaling 1. And this is another possible antiderivative. This is f with f of 0 equaling 2. Okay, so those are three possibilities. Okay, we're going to do another one, which is a little more complicated. I'm going to draw the function first. The scale is going to be different on this one. 10, 20, 30. 10, 20. Okay. I'm going to go up like that. And then at 20, we're going to be back at 0. Then we're going to cut down and go back up to 30, like that. Okay, so this is f prime of x. This is our derivative function. And here's what we want to do. Given that f of 0 is equal to 100, we're going to sketch a graph of f of x and show critical points. Okay, so there's the situation. All right. Now, let's just remark what the critical points are going to be. Critical points will be at first, x equals 0, second, x equals 20, and third, x equals 30. Why do I know those are the critical points? Because those are the points where the derivative is equal to 0. Those are going to be the critical points of f. Okay, so let's think about what the graph is going to look like here. $10, 20, 30, 40. Now, we want f at 0 to be 100. So whatever the scale is, right, my scale is not square anymore, but I'm just going to have equal to 100 there at 0. Okay. Now, I need to be an increasing function because the slope is positive from 0 to 10. And at 10, however, I am, see, we're picking up area, right? So when we're drawing, let's think about what f of x is equal to. F of x is equal to the integral from 0 to x of f prime of t dt plus f of 0. This is because we know by the fundamental theorem that the integral from 0 to x of f of t dt is f of x minus f of 0. So I rewrite that in that way. So when I'm thinking about drawing the function f, this function here, I start at f of 0, which is 100, because that's been given to us. And then I'm adding the area that comes up, right? So when I'm figuring out what f of, say, 5 is, f of 5 has to increase from f by the area of that little triangle, right? So I am increasing with area here. But then, right, at 20, I stop increasing area, right? I'm picking up more and more area till I get to 20. Then I stop increasing in area because then I start decreasing in area. And then at 30, I start increasing in area again, right? So I've marked out the three critical points here with these black dots. Now, there's another key thing that we can see from this here. We actually have some inflection points. So this is a critical point. Here we have a critical point. Here we have a critical point. But we actually have inflection points here and here. Okay, the reason for that is we have this sharp change in f prime at those values, at x equals 10 and x equals 25. Remember, a critical point of f is when f prime equals 0. A critical point of f prime is a point of inflection of f. So I have circled here the two critical points of f prime. That's when f prime is equal to 0. Those will lead to inflection points, and we can see that in the picture here. Okay. Okay, so let's take a look at one more problem here. I know this is getting a little long. I apologize. Here we're going to do, okay, suppose that f prime of t is equal to t cosine of t, and f of 0 is equal to 2. Let's find f of b for b equaling 0, 0.1, 0.2, all the way to 1.0. Okay, so we're going to use a computer to do this, right? So we want to figure out what f of b equals, but by the fundamental theorem, we know that f of b minus f of 0 is equal to the integral from 0 to b of capital F prime. So the integral from 0 to b of t cosine of t dt. So that in particular means that f of b will be equal to f of 0, which we've been told is 2, plus the integral from 0 to b of t cosine of t dt. So now if we want to make a table of values, like this, now we're going to use a calculator, or I'll use Wolfram Alpha, but your calculator can do this actually. There's something called fnint in your calculator. Okay, we'll stop at 0.8 just because I've run out of room here. But the way that we do this, right, is we're going to go to Wolfram Alpha. Well, this one I know already, right? Let's do this one in Wolfram Alpha. I want to know what 2 plus integral of t cosine t from 0 to 0.1 is. And let's check and make sure it parses it correctly. That's exactly what we're looking for. 2 plus the integral from 0 to 0.1 of t cosine t. And here it tells us the answer is 2.00499. Now for point 2, then all we do is we go up and we change our query to give us a point 2. 2.0198. And then we would continue with these other numbers. I'll fill these in from a chart here. Okay. All right. So that is our first foray into antiderivatives. Have a look at the worksheet, and good luck on the web work.